Okay. Okay, so one of the things I want to do in the last is to just talk about uniqueness. So what happens when the map is expectation valued, and what can you say about uniqueness of the stochastic variational inequality? Okay, so let's start with strongly monotone maps. Okay, so let f of x omega be strongly monotone with parameter eta of omega, where eta of omega is greater than eta for almost every omega. Okay. So what can you say about the original map, expectation valued map? So if you look at the original so first of all, let me write this out. F of x omega. So if you want to look at this, so you can take the expectation out. So what you notice is that if I said that f of x omega is strongly monotone with eta omega, where eta omega is bounded from below, then f of x, which is the stochastic map, is eta bar strongly monotone. So if you get a solution of the stochastic variational inequality and f of x omega is strongly monotone with eta omega, which is bounded from by eta, the original stochastic variational inequality problem has a unique solution. Now this is a strong requirement, right? It's requiring that this is true for all eta, for all omega, sorry. Can someone tell me how to weaken this? How would I weaken this? Suppose I told you, so here's the result that actually, this is actually the result, a weaker version. So suppose I said eta is greater than eta bar for omega in some smaller set where the probability of omega is just positive, and more generally eta omega is just greater than 0 for almost every omega. So what that means is your game map is strongly monotone only with finite probability and is monotone almost surely. So my claim is that that is all you need. This is strong. The question is, how would you change this proof? So the way to change the proof comes from the integral, right? So let's think about the integral. How would the integral change if I had that assumption? Excellent, Alicia. So what you do is you write two integrals. You have one integral in omega c, where you have eta omega x minus y squared dp omega, plus eta omega, and this is just, in this case this is just going to be 0, omega c complement x minus y squared dp omega. Now we know that this is greater than eta bar x minus y squared times some probability of whatever, omega c or whatever it is, something, right? Right? Because this is all going to come out and you're just going to get p of omega c, and this is going to be greater than 0, so this is just 0. So you get strong monotonicity with a slightly smaller constant. Okay? So for strong monotonicity, you only need strong monotonicity to hold with finite probability. But it can't be 0 probability, it's going to be finite probability, and it's monotone with almost surely. Okay? So let me write the assumption more clearly so that we have the assumptions. So the assumption is if f of x omega is strongly monotone, or eta strongly monotone for omega in omega c, where the probability of omega c is positive, implies that expectation and is monotone for almost every omega, implies that expectation of is strongly monotone. Okay, which implies VIXF has a unique solution. So if you have a game map in the stochastic regime and you're trying to make your assumptions on your constants, all you need to do is make assumptions that ensure that with finite probability the map is strongly monotone. You don't need it for every realization of uncertainty. Okay? So, and that helps you in certain cases. So for instance, if you have increasing costs, you just need to make sure that the costs are increasing for finitely many, with finite probability. For the rest of them they could be flat, right? Now that doesn't really make sense because it's a generator, but you get my point. When you're designing or you're working in your models, you need to make sure there's something that gives you that, because in a lot of settings the community that we're speaking to is interested in uniqueness. You don't want to tailor your model completely for them, but at least you can provide the assumptions that guarantee uniqueness so you can articulate them. They may not always hold in practice, but at least. Now what happens about monotone? So if it's merely monotone, it needs to be merely monotone now a sufficient condition here is if f of is monotone for almost every omega, it implies expectation of f is monotone. Okay, so this is immediate. So uniqueness, so again epsilon uniqueness would work in the same way. Okay. Now remember here, if you have epsilon uniqueness, you only need to put the epsilon for omegas with finite probability. You don't need it for the entire set. Okay. So, and that's this result. The mapping f of x omega of the scenario based game is said to be epsilon strongly or strictly monotone. If it's monotone in an almost sure sense, and if there's a subset u, which is at omega c, with where the probability of the measure of u is positive, such that f of x omega is strongly monotone when omega lies in u. Okay.
If we consider like some outcomes and probability of the occurrence, we can say it's 0, right? But if it's 0, we can also think of it as a probability like 0.0001. It's very, very small.
Yeah, it's so fine. You can have a small probability. That's not the. Remember, this is an assumption that in some sense is a model-based assumption. So yeah, you can make any, because uniqueness is, as long as you get uniqueness, you're fine. Yeah. Okay. Other questions? Okay. Now I want to derive uniqueness of the stochastic equilibrium problem for stochastic perfectly competitive problems. Okay. So the uniqueness follows as long as the gradient of this is a strictly an epsilon strongly monotone map, right? Because remember, whenever you have a problem in 2 dimensions, actually this is incorrectly, this is should be S comma G. So we can see because of this regularization, it's strongly monotone in S. For it to be strictly monotone in G, you need some, you need to have some properties on the cost function, right? So this is what the Nash-Cournot equilibrium looks like. This is the epsilon variant, which is reducible to a shared constraint game. Okay. So now I want to just go through this one. Okay, this is so for this one, let's think about the uniqueness of each of these problems. Let's start with the perfectly competitive. So the perfectly competitive reduces to an optimization problem. That optimization problem, we have linear or nonlinear costs. We have to regularize the sales. If this is strictly increasing, you're fine. If it's not, you'll need to regularize in G as well. So if it's just C transpose G, that's not enough. You need a quadratic term there. Okay. So the perfectly competitive equilibrium, the uniqueness of that follows with a simple regularization. What happens for the Nash-Cournot equilibrium when you have expectations? So when you have expectations of this, now I've put in a shared constraint, which is this supply demand constraint. No, this is not the shared. The shared constraint is here. So you have an expectation based objective. Now the line limit, and so this is a shared constraint game. Okay, so I'm going to be introducing some of this tomorrow, but let me start by doing it today. In a shared constraint game, the shared constraint game, you have an objective like this. I'm just using hi of x, I, x minus I. Xi lies in, what do I use for that? Okay, in k of x minus, so I'm going to use f here, okay, so that, and minus f. So what does this mean? This means that the strategy set that is induced as far as the f, agent f is concerned, is a consequence of what my rivals do, right? So this is defined as the set of xf such that xf, x minus f lie in some fixed set C, closed and convex set. This is called a shared constraint game. Okay, a simple example of that, let me give you. Suppose I tell you that I have x1 plus x2 is less than 3, right? So that's like saying x1 lies in a set k of x minus 1, which is the set of x1 such that x1 plus x2 is less than 3. And 3 represents this, could be, so this is the set. Okay. So what, intuitively that set is just x1 plus x2 is less than 3. This is 3 comma 0, 0 comma 3. This is a fixed set. Okay, assuming x1 and x2 are non-negative. Okay. So now you've got a shared constraint game. And I wanted to start introducing this idea of looking at shared constraint games and quasi-variational inequalities. Let's do that a bit today, and then we'll start doing that tomorrow again. Okay. So So a generalization of the variational inequality is the quasi-variational inequality. So if I gave you a problem like this, theta 1 of x1, x minus 1, subject to x1 lying in some mapping x1 of x minus 1. What is this? This is the feasible region that is induced given rival decisions. Okay? So it's basically defined in the following way. It's defined as the set of x1 such that x1, x2, whatever. If it's a shared constraint game, you can specify this as this lies in some common constraint C. If this holds, then a shared constraint game. Why do I say a shared constraint game? Because all of us share from this set C, right? So if Alifia and I are competing, Alifia is at x2, then I have to be at x1 so as to meet this requirement, right? If you're all collectively doing it, it's like sharing some common good, okay? Now, more generally, there is no requirement. It's just, you know, x1 of x minus 1 could be C1, and in the case of if Jing had her own constraint, it could be C2. That is a non-shared constraint game. Each of us has our own resource requirements. Okay, so now that we have that, then the question becomes, what are the equilibrium conditions? So what do we need to assume there? You need to assume that x1 of, now, so this becomes a little more complicated, right? So let's do it in terms of I. Now, these are now set valued maps. What is a set valued map? A set valued map takes as an input some vector and spits out a set, right? As opposed to a single valued map that takes in a vector and spits out another vector. Okay, so this spits out a set. So what is the domain of xi? Xi lives on the domain of x minus I, which is j not equal to I, j not equal to I xj. This is not the best notation. Let me think of, let's say xi lies in ki. So xi, let's assume that, actually let's assume this thing is in the real line, okay, just to make it easy. So this is n minus I. What is this? R of n minus I is R of summation of nj, j not equal to I. And it gives me, I'll put a double arrow to show that it's a set, to Rni. Okay. Now, what we also need is that this image is a convex and closed image. So if I gave you an x minus I, you should be spitting out a set which is convex and closed. So for instance, if you spat out an image that looked like this, would it be valid? No, it's a union of two closed and convex sets. It's clearly not convex, right? So that's not allowed, right? You need the image to be convex and closed, right? So for instance, if I gave you this, not valid, okay? And then once I have a convex and closed image given x minus I, this is some fixed object. If it's a fixed object, then the solution of this is going to be just a vi, right? It is captured by a vi. And what is that vi? It's yi minus xi transpose the gradient of xi times theta I for all but as far as you're concerned, this is a constant set. It's not changing. Okay? Now the problem occurs when you stack them together. Once you stack them together, what you get you want a joint solution, you get y1 minus x1 transpose gradient of x1 theta 1 Okay. So now it turns out X is a solution of this coupled system if and only if y minus x transpose f of x is greater than 0 for all y in the Cartesian product of xi x minus I. Okay? And I'm going to write this in this following fashion. Right? I'm going to write this as just y in k of x. Right? So if you think about this, right? If I get you an x, essentially the x has to satisfy this, right? What does this mean? It means it's a fixed point, right? So you're looking for fixed points associated with this Cartesian map that satisfy this requirement. So that tells you how hard this problem is, right? So the quasi-variational inequality problem is hard for a host of reasons, not least of which is the fact that, you know, underlying this is some constrained fixed point problem. So it's a nasty problem to begin with. Okay, the shared constraint version is a little easier. Well, it's not easier, but the thing is that the assumption that we make or the focus that we have makes it a little easier. Where did I keep it? What did I do with the? Yeah, I was just using it. Oh, there it is. I've not dropped it there for a while. Okay, so this is exactly what it is. K of x is the product of kf of x minus f. And I'll do this again tomorrow. So don't, I know it's the end of the day today, but I want to just start introducing this. So then,
one quick question.
Yeah.
Is there no condition for the mapping theta I xi x minus I of convexity or
so you need the theta I as before. You need theta I to be convex and xi for any given x minus I.
so x minus I as considered parameter for
Yeah, you need that. If you don't have that, you can't even go from there, right? So whatever conditions you had for the VI, you need here, right? But you need more later. So the QVI, the VI, this was constant. But the QVI, this is quasi, this becomes K of x. Okay, so it's harder. Now what happens when it's a shared constraint game? If it's a shared constraint game, and this I'll tell you tomorrow, I'll give you more details. In the shared constraint game, the set, because look, in the shared constraint game, this has a very specific structure that you're sharing this constraint, this set C, right? And once you have that, you can restrict your new set for the VI into KF intersection C. So it's a constant set. So you can solve a VI over a constant set. But if you do that, you get a very specific type of equilibrium called the shared constraint or the variational equilibrium. Okay? And tomorrow I'll give you some insights about why that's true. Okay? Now, why is this easier? It's easier because it only requires solving a variational inequality problem. You can show lots of properties for the VE, but you know the thing is that there might be other equilibria looming like that you're not able to say anything about. But that's something that you live with if you're okay with that. Okay, the uniqueness of this variation, and so if you have some properties on the price functions, then you can actually show that the variational equilibrium under suitable regularizations is indeed unique. Does not say that the generalized Nash equilibrium is unique, just says the variational equilibrium is unique. Now, if you wanted to focus on the generalized Nash equilibrium, I can give you some references. You can directly look at the primal dual map and analyze that. In some cases, you're able to get existence for and uniqueness for something larger. I don't know about uniqueness. So existence you can of course show from variational equilibria. I'm trying to think what we did. I should check that one last claim about uniqueness, whether we have something. For a particular market we did something, but I can't remember. It's been a while. Let me check that. So let me just tell you which references are useful from the standpoint. Of course, this is, as I've told you, is the main one. If you want to look at stochastic approximations, this is the first paper on stochastic approximation on stochastic variational inequality problems, okay, by Wei-Fu Xu. There's been work done on sample path or sample average schemes. So this is the paper where we actually looked at the coercivity results for non-smooth convex Nash games. The volume by Alexander Shapiro, Darinka, Dencheva, and Ruzinski has tons of results on stochastic approximation, and there are more references. There's a two-stage, yeah. So this paper looks at using sample average approximation methods. This one, Zhang, Xu, and Wu. Okay, and there are more. I mean, we've done a fair amount, and others have as well, on stochastic, on approximation approaches for stochastic variational inequalities. Wei-Fu Xu has done a lot on sample average approximation schemes, and of course Alex Shapiro has done a lot as well. Okay, so I'll stop here, and what I wanted to do is I've actually got code now. So one thing I wanted to talk about is, so I wanted to ask Jalal, I forgot to ask him in the break. So how many of you have know much about, so yesterday when we talked about these marginal cost pricing and the notion of generators, do a lot of them know about the modeling of these from the standpoint? So I have a presentation which I thought I could give, just to give you an idea of the model, give you some intuition of these models when you have, because one thing that I felt would be useful is, so let me just show you what I mean, and then you can see if that's, so this is a presentation I developed a while back, and I thought I could just, so what I thought was that I could just show you, because I have a fair amount of insight here on the optimization model. So do you think this would be useful? So let me show you, and so the idea is, I'll go towards the end, but I want to show you why you have that the price is equal to the marginal cost of the cost of the marginal generator, give you some insights about these things. Okay, so we'll start with something quite straightforward. We're looking at the day ahead process. We have day ahead bids and offers, generation offers, demand bids. So there are a host of problems. I'm going to look at, for the time being, just a single shot real-time market. Okay, so you have, when you have the real-time market, you have essentially transmission constraints, you might have generation offers, but the main result is locational marginal prices. Okay, and I want to make sure that you understand where these prices come from and how they relate to Lagrange multipliers. Okay, so so all of you must be familiar with the economic dispatch problem. The economic dispatch problem is solved every 10 minutes, 5 minutes, whatever it is, based on the market, where the dispatch quantities are chosen to meet capacity and flow constraints, right? And these dispatch quantities minimize the cost of generation. Okay. Now what happens is that every generator submits an offer that goes from Qmin to Qmax, and this red curve represents the kind of offer schedule, right? So it says I'm willing to generate this much at this cost, then this much at the next cost, and so on. Okay, so these are offers that are submitted, right? So you have a bunch of offers coming in, and now once you have these offers, they get added up. Once they get added up, you get this kind of supply curve, some supply curve, right? And then where that meets demand, you get the clearing price, right? This is all, all of you must have seen this in your courses. And then you have this notion of the cost and the producer surplus and so on. Okay. Now, the producer surplus captures the excess that each dispatch generator gets in excess of its offer level, because I might offer at this, but the price is here, so I get that incremental amount. Okay. How many of you have seen this kind of stuff before? Most of you have seen it. Okay, so I'll move through it faster. So all of you know about LMPs? How many of you know about LMPs, locational marginal prices? Okay, a little less. Okay, not as many know about LMPs. And you know about, okay, so now you have the nodal LMP represents the cost of meeting an incremental unit of load at that node as captured by the incremental cost of production, right? And it's an output of the economic dispatch problem, right? So when units are dispatched, and every unit is at one of the following: Qmin, Qmax, and between Qmin and Qmax. So if you're at the max, at the, oh, I flipped this. This should be here, that should be there. So these are called marginal units. So if you have a generator, the generator, if it's switched on or it's dispatched, then it's at Qmax, or if it's being dispatched and it's costly, it might be at Qmin, at least the minimum level, or it might be between Qmin and Qmax. Okay, and marginal units define the locational marginal prices. And this is something that I worked with some of the students yesterday. So you understood why the price was exactly equal to, and I want to show you that again today. Okay. Let's start with a simple two-node network. Okay. So in a two-node network where you have two firms, two generators, and what you have is essentially, that's the capacity and that's the marginal cost, right? Now, if you look at this, that's the line capacity here, 100, and this is the requirement, 80 and 125. Now, clearly the aggregate demand requirement is 205 and the aggregate capacity is 250. Okay. So if you look at this, what happens is that essentially if you look at this, what happens is that you have 80 unit. Now, what's cheaper? This guy is cheaper. So you have 80 being supplied here, 70 is sent across, right? That's 55 left, and the remaining 55 comes from here. Okay. So the LMP corresponds to the marginal generator. And what's the marginal generator? The marginal generator is this one. Okay. Now I want to make sure that everybody understands that's the intuition, right? But why does it occur in mathematically? Why is it that the marginal generator always generate? Why is it that the LMP corresponds to the price or the cost of the marginal generator? So let's try and understand that just mathematically, right? That's economic intuition, but it should be reinforced. So is that something that you guys have seen in your classes? Why is it that the price is equal to the margin? So let me just do it for those of you who haven't seen it. So if you remember, when we solved this problem, it was minimize Ci of Qi, and you had Qi less than cap I. The Lagrange multiplier was lambda I for all I, and where summation of Qi is equal to D. This was the price, and Qi was non-negative. Right? What are the KKT conditions of this? It's Q1 orthogonal to C1 plus lambda 1 minus P greater than or equal to 0. Let's assume that this is the marginal generator, okay, 3, just for the heck of it. Okay. So now, if this generator is on, and you are going to assume that the C1, C2 and all are distinct. So you won't have two generators on at the same, with the same cost, right? So if this generator is not marginal, but has been dispatched, what do you know? You know Q1 is greater than 0, and you know Q1 is equal to cap 1. Agreed? So if this is true, then you have lambda 1 is non-negative, which means that, and since this is greater than 0, we know this has to be satisfied with equality. So C1 plus lambda 1 is less than, no, I'm sorry. P is less than C1 plus lambda 1, right? Similarly, C2 plus lambda 2, oh, I'm sorry, this is equal to, I apologize. Whatever I mean. Okay. And then the last one is C3. Now, in the case of the third one, what happens? Q3 is positive, but Q3 is less than cap 3.
Yeah, so that would be.
So lambda 3 is 0, which means that Q3, sorry, C3 minus P is equal to 0, which implies that P is equal to the marginal. Okay, so it's not difficult for you to figure out that the price is equal to the cost of the marginal generator, and that's exactly what you see here. Okay. Now, a question that was raised yesterday is what happens when you have quadratic costs? How would you do it then? Can you come up with something with quadratic costs? Right, so the way you would do it is you would have D1 Q1 here and whatever D3 Q3 here. So then what you need to be careful about is now if you look at this is going to be what? D1 cap 1. This is going to be equal to D2, the second one is P is equal to C2 plus lambda plus D2 cap 2 because the other generator is also at capacity. And in the last case, what you're going to get is P3 is equal to, the lambda is 0. So again, it's equal to C3 plus D3, whatever the Q3 is. And what is this amount? This amount is going to be the residual demand. It's going to be equal to the demand minus Q1 minus Q2. Right, that's the residual demand. Does everybody see how to deal with the quadratic cost? Somebody asked me about quadratic cost yesterday. It's a little more complicated, but not too much. Right? It comes from the KKT conditions. Okay. Okay. So now, so the sensitivities of a variable to the power flow. So the more common sensitivity factors, PTDFs and loss factors. I don't want to waste too much time. But what I want to do is, okay, so PTDF is something that you already know about. This is not something I'm going to spend time on. What I want to do is this problem. Okay, so in this problem, again, remember the cost of generation, the power balance. You have transmission constraints, and you have generation limits. Okay. Now, let's go back to our example. We have a load of 100 megawatts, two generators with offers of $5 and $10 per megawatt, and the capacity of one is 60 megawatts, the capacity of the second is 80. What is the dispatch level to minimize cost? Okay, so supply equals demand is P1 plus T2 is 100, right? And we need P1 to be less than 60 and P2 be less than 80, right? So you have this. So for those of you who have not taken linear programming, this is a graphical representation of the feasible region, right? So this is P1 plus P2 is equal to 100. So you need to be on the purple line, right? And you need to basically be feasible with respect to these curves, these lines. P1 less than, so you need to be on this side and you need to be below this, right? So now, and you need to be greater than this because P1 is greater than or equal to 0 and P2 is greater than or equal to 0, right? So that's the feasible region. So does everybody see why this is the feasible region, right? Because you have to be on this line and you can't be here because you violate this constraint. You can't be here because you violate this constraint. You have to be on this constraint because this is the demand requirement constraint. Okay, is that clear? The question then becomes, what is the best choice from here, right? And that is something that you can derive from the cost function. Okay, so now you have the cost function. That's the cost function. 5p plus P1 plus 10p2. What is that? That's the cost of generation of generator 1 plus 10 times the cost of generator 2's dispatch level. Now when you have it at this point, that's equal to 1200, and what you find is as you keep moving, you can see the cost function keeps going down. That's the geometry of a linear program. At some point you're going to find that it gets minimized, and that's at this point. Okay, and that's the optimal solution. So there's a beautiful geometry regarding the solutions of linear programs and optimization in general. But does everybody see this? In a two-dimensional setting, it's very easy to see. You can get a polyhedral region. You start the objective function plane from the increasing side and keep dropping it. At some point, it's going to touch the feasible region, and that's essentially the maximum value. You keep going till it just leaves the feasible region, and before that, you just back up and you get the minimum cost. Okay? Is that clear? So that's a linear program, and those are the decision variables. These are the constraints, and this is the metric to be minimized. Okay? So the shadow price or the dual variable is associated with the constraint. Now I want to make sure everybody understands this. If you look at this, if you change the constraint slightly, what happens? The cost reduces from 700 to 695. A slight change in this constraint. So if you change the binding constraint, which constraint is binding? This constraint is binding. If you change this from 60, relax it by 1 unit, make it 61. What happens? Essentially what happens is the cost reduces. When you relax a constraint, you give the system more resource. If you give it more resource, the cost should go down. The cost goes down by 5. So what happens is the Lagrange multiplier associated with this constraint is 5. So that's the intuition of a Lagrange multiplier. A slight change. Now it won't be exact, because remember this is at the margin. It's a gradient. But here you can see a slight change, it's exactly 5. Okay, a unit change in the constraint leads to a drop in the cost in accordance with the shadow price. The term shadow price, Lagrange multiplier, dual variable are all interchangeable. Okay. So now if you have no capacity constraints, then the lambda, beta 1, beta 2 represent the shadow prices associated with the appropriate constraints. Okay, no capacity constraints. At the optimal solution, how are the shadow prices related to optimal dispatch quantities? You can just do this by writing out these linear equations. Okay, it's not difficult to do. Okay. Now, here's the insight. Without the capacity bounds, there's a fundamental relationship between the shadow prices and the bids. Okay. So suppose let's consider some problem instance. If P1 is a capacity of 50, and I put a bid of a capacity constraint of 50. Then what happens? So then you get a solution like this. Now if you think about it, if this constraint is active, then the new shadow price, which is the price, which is a Lagrange multiplier, this is going to represent the price at that node. This lambda, when you write it out, is now dependent on the shadow price of this constraint that is active. You see, this constraint. When we didn't have capacity constraints, this alpha didn't show up. Now it shows up. And you can see what's happening. You're getting an additional amount here, alpha 1. If you take lambda to the other side, it's 5 plus alpha 1 minus beta 1. Okay? And so now let's look at it. 2-node example, right? Now what happens is that if I impose this, if I put in a new, if I change this, now when I send this amount, I can only send 60 amount across because of this. So previously I could send more, right? But now I put in a capacity bound here. When I put in a capacity bound, there's congestion. When there's congestion, the transmission price changes here. So you can see the LMPs are different. Okay. So if I wanted the marginal here would require me to, because look, I only use 140 units here. So if I have an extra unit that I need here, I'll just service it from here, and that cost is 10. If I need an extra unit from here, I'll service it from here, and that cost is 15. Okay. So there's the intuition is that the difference in LMPs is a consequence of congestion, and that congestion is something that is naturally occurring when you have capacity constraints that are binding. But what you have to remember is it's not just economic, it actually shows up in the mathematics. If you look at this congestion, it shows up because that capacity constraint is binding. And that Lagrange multiplier shows up in the KKT conditions. It's a non-zero value, and basically the price is no longer equal to the marginal cost. Okay? Okay, so I didn't want to spend too much time on this part because this is more specific to the markets in the US where we have marginal energy prices. But what I want to do is go ahead because these are very specific kind of questions. Okay, so what I've done now is I've got code developed for this network. Okay, so this is a small network which I developed for one of the grid operators. And some of you guys might have played with this, but I just want to get people familiar with it. So what I'm going to do is send you this code and we'll start making sure that everybody can play with it and we'll just understand it. Okay, I'm not so interested in you sitting and coding this because this is going to take a little bit of work. But I want you to have the code so you can run it and we can play with it a bit. Okay. So what we do, and let me go through this. Okay, so I'm going to send you the code and you guys can run it and then we'll just see, you know, while we're doing it. Because what I do is I've got several instances that I've been running and I want to make sure that you see these instances and you can appreciate what's going on, but you have the code.